So, hi everyone, welcome to the second week of the infinity category or the higher category reading seminar. So, today I'll be speaking about nerves, infinity categories, and the Boardman-Vogt construction. So, basically, the last three sections of the first chapter of Cisinski's. So, here's the plan. So yeah, typical stuff. All the things that are there. So, but if time permits, then I'll also give a definition of Siegel category, like just briefly. We do that for just add. Okay, cool. So yeah, so let me start with a bit of motivation. So I'd like to start with the notion of a classifying space. So a classifying space is like so for some sort of data and information that you have. So classifying space is like a space such that the arrows that are coming to it from your object of interest correspond to the data over that object, right? So the nav is like, so it is like a classification space of a category, right? So let me give a definition. Associated to category is the simplicial set and this is the category of small categories, cat. So again, I'll repeat. So if there's something that I mess up or if there's something that's not clear, please just speak out. I may commit mistakes. So okay. So also we can like think of the nerve as like so we can think as follows. And so it consists of strings of uncomposable arrows in the category. Right. So it's like a poset category. Right. And now because it's a simplicial set, we have the notion of face maps and degeneracy maps. So let me define them. The degeneracy map takes a string of uncomposable arrows, say, right, to a n+1 string by attaching an identity map. Right? So maybe maybe I'll draw this I place. Right. So if we draw it, if this is our string that we have. So let me define it with this. So the degeneracy map, so we'll just add an extra identity morphism in between. So I type this because it is right. And the face map, so the face map is a bit more, it's not as straightforward as the degeneration map.
I think up there when you wrote FI, it should be identity, right?
Oh yeah. Thanks. Yeah, mistake. Thanks. And the face map basically. So typically, so it composes the. So maybe I'll write it down as well. So it composes the I and the I plus one arrows for it. So I inside the open interval, and if I is a zero or not or n, it just deletes the ith object with the associated arrow. So maybe I'll just draw it for the case when it is between 0 and n. So hope there's no problem with the handwriting so far. Okay, so the degeneracy map for 0 for I between 0 and n. So it just composes the. Right, and everything else remains the same. Okay, so in Cisinski actually, so there's some motivation there, and so why should we think of a category of poset? So Cisinski notes that we have a fully faithful functor from the simplex category to the category of sets. So maybe, yeah, Cisinski calls it an I. And then the nerve functor. Nerve functor is just the evaluation at. So maybe I star. Yeah, I star. So again, so at some point we'll also prove that the nerve functor is also fully faithful. So now again, now using Kahn's theorem that was proved in the first week. So by Kahn's theorem, discussed previously, so it has a left adjoint, and that is something that yeah, that is something that we will postpone for a moment, and we'll look into that later. So turns out this gives us so this is the way we get the homotopy category out of a central set. Some people also call it the truncation, but yeah, we'll realize that this gives us the homotopy category. Right? So thus we have this subtraction. Right. So now, yeah. So now for the simplicial set, X, the objects are the zero simplices. That is, which can again be seen as maps, and morphisms are one simplices, which are again maps until one X. Now, all right. So now we'll kind of see how we we interpret the targets on source maps. So suppose we have we have an arrow. So we have an arrow that arrow in the category that is an edge, which is an edge in the simplest set. Then the faces of F are given by so the target will be the maps that we defined before. Source. So maybe I would draw. So this is our map F. Hope this is correct. Right, so this is the way we can see things, and so and now for an object, say for an object of X, so the degenerate so the degenerate edge, that is this, so that is the identity morphism. It's the morphism. Okay, cool. So now what I'll do is, so let me recall the definition of, so let me recall the definition of a standard n simplex. So for n integer variables are equal to 0. So yeah, so the standard n simplex is the simplicial set, which is given by the construction, by the following construction. So take an object, just map. So this is the construction. So the remark is there again for an integer variable 0. So the nerve of this ordered disposit can be identified with the standard in simplex. So now as Cisinski does, so there's some notation to be introduced. So for a finitely totally ordered set, we denote right. So now we have a definition of so we have like definitions of the boundary and boundaries and horns, and we also define spines as unions of these different sets. We have so yeah, so maybe right. So this is the boundary for the horn. So something without the key. So this is so these are the ones that so this is exactly how it's done in Cisinski. And yeah, so there's also so first yeah I'd like to define so spine. So the way I see it, so it's actual definition. So you can also define spine that. So recall spine is a simplicial set whose case is monotone maps. So maybe I'll call it sigma with the bound. Right. So like yeah, so we kind of have an identification. It's really annoying. Not sure how I have an infinite number of pages. So yeah, so you can identify with discrete graph of this form. And in Cisinski, so there's also a similar definition of the spine. So you define as a union of these sets. So now I'd like to introduce, so I'd like to define a simplicial object. So that has to do with the example that I'm thinking of. So there's an example of the law of construction that I'll be giving. So maybe I'll just give a definition of the simplicial object. So simplicial object X in a category C. So it's just a simplicial set that is internal C. So now when we're so yeah, maybe a few words about internalization. So it's like so when we are thinking of an internal category so we can think of internal category of categories which are uh, which have sufficient number of fullbacks, and so it has an object associated to the objects of the category, an object associated to the morphisms. Yeah, so it has similar. So it has these source and target maps. Then it has a composition map and all these things. Maybe I'll not get into the details. So and a few other conditions. So that's the general notion. So it is something that is quite broad, I would say. So that's the definition. So now, so the example of a now that I'll be giving is the church now. So so let's consider category with pullbacks. So looking for C and a map and an arrow in the category. So maybe I'll call this to Z. And right. So the church now is the simplicial object in C such that so the degree case maps are given by the k plus 1 fold fiber product. So so maybe I'll write it here. The k fiber product is given by the. I hope I said that. So, yeah. so that's so that's all. Yeah, that's all the examples. Now, so now maybe yeah. So now I'll be defining triangles. So so triangle in a simplicial set is a map with boundary. So yeah. So it can be seen as a. It can be visualized or just maybe right. So that's the way we think of it. So as a triple where these are morphisms in there. Uh, so these are morphisms in the predicate with, so there are a few conditions with target. So with the target of F coinciding with the source of G and the source of F and H being the same. And G and H have the same target. So So yeah, from the previous definition of the boundaries as a union of these equation sets, so we can write. So So yeah, so we can kind of see. So yeah, it will boil down to so we'll get a triangle like this. So this will look like this. I'm not wrong. H. So this will look like this, and so and yeah, so if so you'll have these correspondences. F will correspond to maybe and yeah, it'll be a decent exercise to kind of think of it like the way it comes out. So F corresponds to the map. This map, and similarly G corresponds to this map. And similarly H corresponds to yeah. So maybe I'm not right everything. So yeah, so we can have we can again. So similarly, we can see a horn similarly as a map also from the we can also see a horn like that. So maybe I'll just draw it as a map from the from this. Okay, so maybe I'll just draw it. So yeah, so this is the way we see it, and yeah. So now, so we have a definition. So a triangle is said to commute if morphism, if there exists a morphism whose when it is restricted to the boundary, coincides with. So maybe I'll draw it. This restricted. So that's the definition. So now, now maybe I will say a few words about the Grothendieck conditions. So yeah, so I'll not get a lot into the details because maybe it's not very relevant for the. I mean, it's important, but so you can maybe well, maybe get into that. Maybe get into a digression at some point later. So maybe I won't speak a lot. I mean, I won't speak in details. So I'll just talk briefly about it. So the idea is that. So the basic idea is that. So we are interested to prove uh, a simplicial set is the nerve of a category if it satisfies some conditions, which are the Grothendieck-Siegel conditions, which I will maybe write. So simplicial set satisfies so the nerve of conditions. So if we know a category. And that satisfies the totally Siegel condition. So in many places in the literature, it is mostly called Siegel conditions, but originally it's due to Grothendieck. So there's a paper, and I think there's an English translation available. Maybe I'll post a link because it's really it's worth reading. So okay, so maybe I'll continue. So satisfies the Grothendieck zero condition if the restriction belongs to some induces a bijection of some sets. So if you have this projection for all n, no, for all integers n greater than 2. So in fact, so maybe I'll also give a sketch of how to prove it, or maybe just to think about it, because it's quite natural. So if so, as I said, I mean from the definition, so maybe maybe it's pretty obvious. Maybe yeah. So if so, I won't call it a fact then. So maybe a consequence. So if n is the nerve of a category and C is a small category, so I don't mean to repeat writing that again and again. So C is a small category. So then basically, so now maybe for I'll just say a few words about when n is equal to 2. In order to see this, so when n is equal to 2, so the objects and arrows of the category of the sequential set, so they're the objects and arrows, so they're precisely the objects and arrows of the category. And so similarly for the commutative triangles in the sequential set, they coincide with the commutative triangles in the category. Right. So in that way you can see this. So right. So now comes the important lemma. So I'll prove that proposition that the nerve functor is. So again, so maybe a few words before the proof. So it is fully faithful. So there will be right. So in a way, so in Cisinski, so you can so from this thing right here, so you can prove it from this, but I won't do it here. So maybe sorry. Yeah. So yeah, so I won't do it here. So I'll just try because showing that it's a so the functor so there's a functor, right? So showing that it's an injection is a bit straightforward. I won't give the proof for it to be surjection, and then I'll give so for an alternate proof. So there's also a different way of seeing things, and in course of that I'll introduce skeleta and co-skeleta. So that's the plan. So cool. Functor is fully faithful. So proof. So this is what we wish to show. Again, C and D. So we know that C and D are small categories. So we're interested to show that this is a bijection. So we can see that it's an injection. Again, I'll repeat that I won't show that it's I won't prove that it's a bijection. So I'll just give half of the proof for this. So clearly, so let me call this functor something. Let me call it zeta. Right. So zeta is an injection because let's consider a functor. It's a functor in the so C and D again are small categories. Then the zeta of f depends. So maybe I'll just say this that it depends on the vertices and edges of the nerve functor NC. Right? So by definition. So that's where the surjective that's where the injectivity follows from. So maybe I'll write this because it's too straightforward. And so I'll now give an alternate sketch. This also follows from the fact that the nerve instruction. So it gives us a two co-skeletal simplicial set. I'll explain the implement. So two co-skeletal simplicial set. So now, so just a brief tool. So I'll just introduce a few things. So if for the simplex category that we have a subcategory, right? And it so the objects are so it's you're just restricting it up to n. So the objects are from 0 to n. Right? So you're just restricting that. Right. So you're considering so you have the subcategory. Then so then this inclusion. So you get this inclusion. This induces a truncation functor. Truncation functor, but I will write this. Okay, yeah, maybe I should write this clearly so that it's more clear. Okay, and so it has so this truncation functor turns out it has a fully faithful left adjoint, which is precisely the end skeleton. Okay, and it also has a fully faithful right adjoint, which is then co-skeleton. I don't know what I'm writing. Fully faithful right. So this is the co-skeleton. So simplicial sets. So maybe a definition. Simplicial sets are category notation. So simplicial sets isomorphic to objects in the image of this functor or maybe range. And skeleton. Right. So yeah, just again, I won't get into the details. I'll just give a brief. So we have this. So you can expand it to get a you can expand the result to get a natural isomorphism from which you can get the result again. So okay. So the proposition that okay. Now I will say a few words about the secret condition. So the exact thing. Uh, the following conditions are equivalent. Again, I won't give a proof for this. It's only notes, but elementary consider followed. So The following statements are equivalent. There exists a small category and an isomorphism, which I'll call isomorphism. Right. So following, so yeah, X is a simplicial set. Maybe I should specify this. And this is invertible. So this is again exactly the way it's presented in situation. Satisfies the growth lake serial conditions. So cool. Now finally we'll get to the definition of infinity category. So defining infinity category. So maybe just to state, so infinity categories were introduced by Boardman and Vogt in the sixth, I think in the late 20th century. Right. So yeah. So they were introduced as weak complexes, and yeah, we'll get to the definition of the complex soon. So yeah. So let me give a definition of a complex. So simplicial set. So simplicial set is a complex. So if every horn, again, I'll maybe say I'll talk about different ways of equivalent definitions as well. So all of them will mean the same, but so we can define an infinity category in different ways. So you have this condition. So every horn can be extended to the n simplex. So this basically means that this diagram, I'm sure everybody has seen. So so you call this filler. So you say that the horn has a filler. So this is the extension condition. So right. So again, a fact that I think I should write here. This is something that just came to my mind. I think it's worth writing. So, but I won't give a proof. The category of Kahn complexes, which is a full subcategory of the category of infinity categories, by the way, is Cartesian closed. So, for those of you who are not, so I'm pretty sure everybody would know this, but maybe I'll just say a few words. So it is just a Cartesian closed category is like a category with finite products, and for every object, so finite products, right? And for every object, so yeah, object of the category C, let me call it C. So this one has right. Right. So that's the definition. So now we are finally defining an infinity category. So an infinity category is a weak Kahn complex. So the way, as I said, so that's the way they've been introduced in the literature. So that was the first name that was given to them. So why weak? Because so it's called a weak Kahn complex because the extension only works. So the extension property only works for inner horn. So it is an extension. Uh, so an extension of inner horns, meaning the inequality is okay. So this to this exists. So again, it's the same diagram. This diagram. Uh, okay. So yeah. So another equivalent way of saying. So equivalent way of stating the definition of infinity category would be so equivalently. So equivalently, or maybe I'll just say this because I don't have time. So equivalently, it's like so I'll just tell like that horns, inner horns have fillers, right? So this is just a different way to state it. Or there's another way, further equivalent definition. There is, so maybe I'll write this because it's not writing very categories as simplifications with right lifting property. So maybe we'll talk about different factorization systems and so and model categories in the next week. So maybe I'll see anything about this right lifting property for inner horns inclusions. Inner horn inclusions. Right. So yeah, so a consequence of the definition again. So again, a consequence would be this map being subjected follows by the definition. It's infinity. So now maybe I'll talk about the object. So the way we work with one category. So for an infinity category, so see objects are vertices. Uh, maybe, yeah, morphisms are one synthesis in C1 and right. And if F is a morphism, so if F is a one simplex, then we have the similar notion of targets and right target and source and target of F. So we again have so maybe I'll define it and a degenerate. Maybe I'll just degenerate edge for a degenerate edge for an object X. It's just this one. So this is the identity morphism for that object, right? So now I'll give a definition. So now I'll talk about infinity groupoids. So an infinity groupoid. So it is just an infinity category where every morphism is inverted. So maybe I'll say what I mean by every morphism being invertible. So if you have a morphism, then there exists maps such that the following diagrams commute. Diagrams. So this is a plus, this is a G. Right. Right. So that's it. Now I'll give a few examples of infinity categories. So if I'm not wrong, I'm running I'm lagging behind a lot, so I don't have much time. So again, for a small category, see the nerve is an example of an infinity category, and the objects are like objects of the category, and the morphisms are morphisms of the category, and similarly the so maybe I won't write it. The source and target of the morphisms of C, they can coincide with the ones in the norm. And similarly, you have the notion of the identity. So another example. So for X, a topological space X, singular complex, so it's an infinity category. So the way we think of it, so the general idea is to think of this geometrical realization, to identify this with the hypercube. So this is the general idea. So again, so the objects are points of the topological space. Morphisms are continuous paths with source being image this and target one. So this is quite annoying. And the identity. So yeah, the identity for an object is just like the constant path. Taking value at x. Right. So in fact, we have the following adjunction formula. So in a way we use it to prove that this is infinity category. We can use it. So this is, I think this is the, so it's there in Cisinski as well. So adjunction formula. Right. So this will so we'll get a surjection along this inclusion. Surjection along the horn. So from this we by this surjection we will get this. So now proposition. So now we'll prove that every Kahn complex is in fact an infinity group of every Kahn complex. So suppose we take a morphism. So we take a morphism and the category X, so X is a Kahn complex. So this is the category of category of infinity categories that are Kahn complexes. So there exists a unique morphism. Right. So this sends, so maybe I'll say this again. So it sends the non-degenerate one simplex of, maybe I should write it. Non-degenerate. It sends it to where and non-degenerate. See, yeah, it sends it to the identity right after. So then we'll get such a commutative. Well, okay, so we can also do it for y similarly. Okay. So now there's a fact. So let let me define the category of groupoid. Then we have the following commutative diagram. And again, as I defined before, Khan will be our category of infinity categories that are Khan complexes. So you have right. So it is like the Khan complexes and now some categories are like so they're simplicial sets with these Horn extension properties. But there are differences. So maybe I'll just say I won't because I don't have time. So the difference is that the differences will be like so all the horns are extended in Khan complexes, but for the nerve construction, we know that they are only the inner horn, the way we define them. And also Khan complexes, it's like for Khan complexes, it's more of an existential statement. And for nerves, it's like the existence is unique, right? So then in the further sections, I think we talked quickly about Milner's work on showing that Amartya theory of CW complexes, it's like Amartya theory of Khan complexes. And so there's a brief discussion if I remember correctly. So now I'll define the off category of an infinity category. So construction. So I'll just give an idea again. I won't get into the details. Let's define a simplicial set. So then X op will be given by the following composition. So you have this composition. And now this map, so for first for these maps and the simplex category. So let me define what this one is. The morphism so it is a morphism which is given by right. So okay, so at the end of this section, so there's a proposition and there's an exercise. So maybe I'll give a sketch to the proof. I'll prove it completely. So for a small category again, for a small category, see we have this identification, right? So recall that the n simplices of are diagrams. So these are these diagrams in the category. Then the diagram. So from this diagram, so you can generate another diagram in the op category. Use instruction, maybe I'll say this. The diagram. The op category. So clearly it's easy to see from this that you have this isomorphism. So you have this equality up to an isomorphism. Right, so this is the brief sketch that I would say. So now getting to the last section. So I think we are already across an hour maybe. Sure. Maybe somebody can verify. Yeah, I think the time. So it's 11. It's 11. So, yeah, I'll just quickly say I want to write a lot of things. But brief. So the Boardman. So just last part. So I'll just give a general idea. So again from the car, so something that we saw before. So to any topological space. Right. So yeah, let me not, or maybe yeah, I'll just give a definition of a fundamental. So a fundamental infinity groupoid. So yeah, I think I've not defined this. So maybe let me first define the fundamental groupoid. So okay, so let X be a topological space. Then for any topological space, define. I did talk about this before. To be the fundamental groupoids. Maybe I'll write this groupoid of X with objects being points in X and for Y in the category. So the Hom set uh, can be identified with what we classes of the constant of continuous paths. I don't know why I said constant. What we classes continuous paths. Right. With again this source, source and target. And composition, I'll just say this composition, or maybe composition is by concatenation. So now so thinking of an infinity category, we think of infinity, fundamental infinity groupoid. We think of a refinement such that the objects are points in X, the way they would go, and morphisms are now paths in X. Then two morphisms are homotopies between paths. Yes, I'm getting sloppier. Homotopies paths and higher morphisms are like higher homotopies. So maybe instead of doing what Cisinski does, that is, so in Cisinski is very sure, so it's so the maps, so these maps, skeleton, so study, such that you have, so yeah, that's the way it's being done. So it's done, and after that you have this, uh, Joyal's lemma, Joyal's coherence lemma. So maybe I'll just draw it. Just draw it. So okay, so the non-degenerate. So because it's a skeleton, so the non-degenerate simplices have dimension less than equal to 1. So we have the following diagram. So maybe I'll just draw the diagram. Right. So this is the diagram. So and then so we define a triangle. So corresponding. So I'll just okay. Corresponding to restriction of x2 of maybe I also. Restriction of it's restriction of x, restrictions of x to the subcomplexes. This category k, where k is like, so okay, maybe I'll learn this. So this will be the 0 of x, this will be d3 of x, and this will be d2 of x, and the whole one will be d1 of x. So basically, Joyal's coherence result, I won't give a proof because I'm already over time. coherence lemma is like, if these triangles and okay, these commute, then so you have this implication, bidirectional implication. And only D2x commutes. So again, so it's like, so by definition, so maybe just give it. So it's not a problem for me if I speak for like 15 more minutes. So it's the same for everybody,
I think you're
or
fine. If people
maybe,
need to leave, they can check their recording.
sorry?
I think you're fine. If people need to leave, they can check the recording.
Yeah, exactly. Yeah. Okay, that's right. So yeah, so if somebody wants to leave, they maybe. So okay, where was I again? So yeah, so by definition, so the way I defined so triangles to commute. So maybe I'll just go to that page where I define. So the definition of a triangle. So this, right? This is what we mean. So we'll use that for the triangles that we know commute. So we know that we know that these two commute. So we'll have these. So we have these triangles. Right. So now if we're assuming that this commutes, if we assume that we'll get this diagram. I mean, then again we can show, so we can show that we can, from this we can extend this uh, to x commutes with, so we can define now, so we can define y2 to be, so maybe I should write it down properly. So we get a morphism. So the way it's done, I mean, it's exactly the way it's done. Which again extends to this, so it extends to the phasing text. So this diagram also commutes. When you define, so let me call this function something. So maybe yeah, this now yeah, I call this y. So okay, and for the other way around, we can just so other way around for that just say it. So conversely, so you can prove that the other way around. For that, just use the same construction, the off. And, so yeah, so that way you'll get the other thing. So now I'll give a definition of a homotopy category. So we'll get to the key isomorphism after that. So okay, or okay, maybe I should give a definition of a homotopy first. Let me consider maybe. So, alright, I'll just give a definition. First, I'll start with the definition of homotopy. So, homotopy can be so two morphisms. Right, these are understood to be objects in the infinity category. In an infinity category, say C are homotopic, which we denote by this symbol. If there exists two simplets, so let me call this lambda with so right. So with the boundary being that is, so maybe I'll just draw this. So this lambda is then called a homotopy, and it's usually written like this. Okay. So now, so there are different equivalent ways of defining a homotopy. So I'll just write it in table 2. So the following relations are equivalent. So you can see a homotopy in different ways. Relations are equivalent, and that is something that the proof of the Boardman-Vogt theorem boils down to are equivalent. So yeah, we can draw diagrams like this one, but yeah, I'll just check. So these are equivalent. So that's the statement. So we have, yeah. So yeah, now we have a proposition that it's an equivalence relation. Again, I want to do a proof. Equivalence relation category for objects, right? And this is an infinity category. So, and homotopy classes of snap is denoted by this. Right. So now we are in a position to define a homotopy category. So C is an infinity category. Then so there exists one category, or maybe an ordinary category with same objects C and morphisms being homotopy classes of morphisms. See, morphisms, homotopy classes, and see, and we can define. So the composition can be defined as follows, and it satisfies all the desired. So the things are associated with an identity that we have defined like this. So, yeah. So now I'll just state the Boardman theorem, and so the key thing for me, the key takeaway from this theorem is that it's the isomorphism that you get. So you have this realization factor, and that is isomorphic to the homotopy category. So that is the key. Right. So there exists. So this is something that I'm not proving. Unique map. So again, you can look it up, which is identity and objects, and which sends morphism in. So maybe this is X towards body class, right? And so the main thing for me is this. Right. So for the proof, so the proof is basically, maybe I'll just say a few words. So it is so at the end of, so there's a remark that Cisinski makes where so it is just like So it just says that, so it explains that you kind of understand maps to nerves of small categories as like, so if you have a simplicial set and a small category, right? So then a map from the simplicial set to the nerve of the small category can be completely determined by a map from a one. So there's a map from a one simplex in X from the category from one simplices in X to the functor category of the one category. So yeah, so you can prove it. That's basically the remark that you can use to prove this part, and this will follow from that. So last few things. So a corollary, an important corollary will be an infinity category. X is an infinity groupoid if you have, so this one is also, so it is a groupoid. I mean, by groupoid I mean one. So right. So so now just the last few things. So a functor between infinity categories X and Y, right? It's just like morphisms between the simplicial sets. No big deal. Right. So you have this, so you can maybe draw a few diagrams of, so you can see the, so for a couple of these the functors, you can see the natural transformation from F to G as this morphism. Maybe I'll also draw the diagram where just define this, and we have this diagram. Well, I'm not sure if I'm drawing this guy. Again, if there's a mistake, please say it loud. This is the way to picture it. So a quick example maybe would be quick example for a topological space, and a small category. So this one, so I won't get into the details again. So it is a functor of infinity category space. So this is an example. So now the last thing. So so we say that a morphism in an infinity category is an equivalence if so this map, if it's an isomorphism, right? So that's the conclusion. I think it's essentially is illustrated in an equivalent way. But yeah, I think that's it. I'd stop. And apologies for extending it to, I think 20 minutes over schedule. So as we are already over schedule, I was thinking of maybe motivating a definition for Siegel spaces, but I'll do that. So
We can push that to next week, probably.
sorry.
We can probably push that to next week.
Yeah. So next week we'll move on to the second chapter. That is the model category. So most probably we'll get to model categories next week.
Does who wants to present next week, or did we figure that out already?
So I think maybe you can stop the recording now.
Oh yeah.
We could ask in the Discord about chapter 2, or I could talk